Hello and welcome to this video. Today we will solve the exercises 31, 32, 33 and 34 of chapter 2 from the book Contemporary Abstract Algebra, 10th edition by Joseph A. Gallian. The question 31 is the integers 5 and 15 are among the collection of 12 integers that form a group under multiplication modulo 56. List all 12. So first thing which we know from the statement is total 12 elements are there in the group. So we have to find the remaining 10 because two elements are given 5 and 15. We know that in a group whenever we will multiply two elements again we will get the element of group. So let G be a group, the required group. Okay, because this 5 and 15 both belong to this group, then of course whenever we will multiply 5 with 5 which is equal to 25, and of course 25 is congruent to 25 modulo 56, so this 25 belongs to the G. Okay, we write here the required group G. There are 5 and 15, two elements are already there, and next which we find is 25, it is also in the group. Now of course because 5 belongs to 25 belongs to G, then 5 multiplied by 25 which is equal to 125 which is congruent to 13 modulo 56. So we get another element which is 13. Now 5 multiplied by this 15 which is equal to 65, and that is congruent to 9 mod 56. So 9 is another element. Okay. Now we multiply this 5 with 9 which is 45, and 45 is congruent to 45 mod or modulo 56. So this 45 is the element. So far we have found 6 elements, and now 5 multiplied by 45 which is equal to 225, and that is congruent to 1 mod 56, and this one will be the identity element of this group. And now we start with 15 multiplied by 15 which is again 225, and we get the same element, so we have to try some other elements. Okay, if we multiply this 15 with 5, because 5 is the element of group G, we get 75 which is congruent to 19 mod 56. So 19 is another element. Okay, and if we multiply this 15 with 9, because we know that 9 is the element of group, we got 285 which is congruent to 5 mod 56. We get another element 5. Now we multiply 15 with 13 which is 195, and that is congruent to 27 modulo 56. 27 is another element. So far we got 10 elements. So still two elements are remaining. When we multiply, here it is 19, not 9. Now if multiply 15 with 9, we get 135, which is congruent to 23 mod 56. So 23 is another element, and the last element which we obtain is or second last. So 5 multiplied by 23 which is equal to 115, and that is congruent to 3 mod 56, and the last element is 5 multiplied by 19, which is congruent to 95, which is equal to 95, which is congruent to 39 mod 56. Okay, so we got, okay, we can see that this 5 is written twice. I was wondering why we got 13 elements. So there are 12 elements in G. We move toward the next question, which is 32. Okay, the statement of question number 32 is, for a positive integer n, let Sn be the set of all 1 functions from the set 1 to n to itself. What is the identity under the operation of the function composition? Does every element of Sn have an inverse in Sn under this operation? Is Sn closed under this operation? Is Sn a group under the operation? How many elements are in Sn? So there are few questions. Since the identity function, which we denote as E, from the set 1 to up to so on n to itself is bijective. So this implies this identity function belongs to Sn, because Sn is a collection of all 1 functions from set to itself. Okay, since the inverse of bijective function f is again a bijective function from set 1 to n to itself. So for all f belongs to Sn, f inverse belongs to Sn. It means the inverse of every function or every element of Sn is also exist. Okay. Next, composition of two bijective functions is again a bijective function. That is, whenever f and g belongs to Sn, their composition also belongs to Sn. So Sn is closed. Under function composition, okay, and function composition is associative. So this implies is Sn is group under the binary operation of function composition. Now, because we have to find all the bijective functions, so whenever we will fix first element and it may have n possible images, and similarly for the second element we have n minus 1 possible images, and so on. This means the total elements in Sn are n factorial. Okay, we move to the next question. The next question is question 33. Prove that every group table is latent square, that is each element of group appears exactly once in each row and each column. So the solution is, we assume on contrary that there exists A belongs to G which appears twice in a row, that is xy is equal to A and xz is equal to A, where x, y and z belongs to G and y is not equal to z. Okay. Because xy is equal to A and xz is equal to A, this implies that xy is equal to xz, and whenever we will pre-multiply with x inverse, pre-multiplication means multiplication from the left side. Okay. What we get is that y is equal to z, which is contradiction. Which is contradiction that we considered y is not equal to z. So this contradiction happens because we assume that A appears twice. Hence, every group table is Latin square. Okay. The next question is question 34. The statement is, give an example of a group with exactly 105 elements and also give 3 examples of groups with exactly 40 elements. So we have just the examples G1, which is equal to Z105. This is a group with 105 elements. G2, this is another group. Z40, we consider this is also the group with 40 elements because we have to give the 3 examples of group with 40 elements. G3 is dihedral group D20. We know that Dn contains the elements 2n. So D20 contains 40 elements, and the last group is G4, which is Z5 Cartesian product with Z8. This is the group with 40 elements. So that's all about today's lecture.